what? You don't have any insulin production. And this represents about 10% of diabetic patients. The other is type 2. And this is, you can have reduced levels of insulin, so you have insulin, say, deficiencies or reduced levels, but most of them tend to be on the pathway we just talked about. They tend to be receptor mutations and problems with cell signaling molecules. And there's a very complicated array of cell signaling molecules. Many of these are active or not active, depending on your age, depending on your health, whether you're exercising, eating good food, et cetera, et cetera. So type 2 diabetes is the adult onset form of this. And this is the other 90% of diabetic patients. They found several diabetic patients that have mutations in the tyrosine kinase, that they have an insulin receptor, but the tyrosine kinase is nearly dead. It's like 95% reduced. Okay? And as we know from this pathway, if the receptor kinase is dead, right, no receptor phosphorylation, no IRS1 phosphorylation, no response. And what comes out of that is a type 2 diabetic patient. There are other diabetic patients that have defects in these cell signaling molecules, activity and levels of expression. A lot of that is more lifestyle related. It's a very complicated mixture. And those of you going on to med school will likely see some diabetic patients that will have some variations of this theme where they're defective. Okay? And they cannot be simply given insulin because the defect is in the cell signaling part of this. Okay? Questions on that? Okay, yeah, back in the back there. Say it loud, I can barely hear you. If the kinase is dead, you still have what? Very good question. The answer is yes. Because the question is, you still clustering if the kinase is dead. View it as a series of discrete steps, A to B to C. If BC transition is defective, AB still works for the most part. You could have feedback mechanisms, but we're not going to worry about that. Okay? Very good question. Yes. Which receptor? I got two of them on the board. Yeah? Do both of what things? Yes. This guy here, say this right here can phosphorylate. Let's just say sometimes these enzymes can be very promiscuous. But in this case, there's examples of that they can phosphorylate anything in sight. This guy has two basic substrates, the other receptor subunit and IRS, and it does them both. Okay? Substrate, you can have enzymes with more than one substrate biologically. Happens many times, many examples. Pardon? I'm not sure of your question. We'll think about it, and office hours are at noon. Okay? Keep it in mind. All right. The other side of the coin of this opposing action is the synthesis of glucose. And this is by an enzyme, a receptor called glucagon receptor. And this is indicative of a set of receptors that pass through the membrane 7 times. So it's a 7-pass transmembrane receptor. And it's bound to a G protein, called a G protein. And in this circle here is the protein. In its inactive state, it is bound to GDP. So this is inactive. Okay? The circle is the G protein. It's bound. It's called a G protein because it binds to guanine nucleotides. What happens then, we'll do this over here, is that the hormone binds on the outside. So here's the 7 passes. Hormone binds. There's a membrane through here. The G protein undergoes a GTP to GDP exchange. So it's an exchange reaction. GDP to GDP exchange. Which results in a form of the G protein with a GTP, which uncouples it from the receptor. Okay? Everybody see that? Inactive state, GDP bound to the G protein. Hormone comes in, releases GTP G protein from the receptor itself, so it's free to move about. What it does is it then binds to an enzyme called adenylate cyclase and activates it. This is now active. Because of the G protein in the GTP-bound form, adenylate cyclase is now active. And what this does is it converts ATP into cyclic AMP, which is a secondary messenger we'll talk about in a second. A series of events. Hormone binds. Let me put this down. It's easier to see this. It's active. The hormone comes in, causes a GTP to GTP to GDP exchange. Okay? You can't obviously make GTP to GDP directly, right? Goes to the mitochondria, all that oxidative phosphorylation stuff. This uncouples the G protein from the receptor and then binds to adenylate cyclase to activate it. 2 points here. The G protein itself is an enzyme. The G protein under this condition has a GTPase activity in it. GTPase activity cleaves off a phosphate group from the GTP, making it GDP. Then it comes back in, binds to the inactive receptor. So it has an off switch. The on switch is the hormone binds exchange. It's active. The off switch is this G protein has a GTPase in its structure, which is now active. Kicks off. Let me make this a little clearer here. Kicks off that last phosphate group and comes back to the receptor and turns it off. So it's an on-off switch. The second point is regulation of adenylate cyclase is very important physiologically, and there are diseases out there that affect this pathway directly. We'll talk about the response in a second. But one of the diseases is cholera. Cholera toxin keeps the G protein active in this active state. So what cholera toxin does is it modifies the G protein. Modifies it in a way to keep it in this active state. So in cholera epidemics, what's the first thing you do in a cholera epidemic? Or one of the first things. What do you have the people drink? Fresh water, right? Because they get this from the water system. And the reason is it's a covalent modification. And adenylate cyclase through cyclic AMP is related to some of the diuretic mechanisms. In other words, getting rid of a lot of water. So the health problem there is dehydration. So it's because the toxin itself keeps this G protein in an active state by covalently modifying the protein. So therefore you have to wait for the turnover. That's why it takes so long to get through these kinds of problems. So everybody see that before we talk about the mechanism or what the response is. Hormone binds, GTP, GDP exchange. You uncouple the G protein on the receptor. It binds adenylate cyclase and activates it. Okay? The cholera toxin, you don't need to know this. the cholera toxin covalently modifies the G protein in a way that keeps it on. So you're always making cyclic AMP. So if you're always making cyclic AMP, what happens? Cyclic AMP, its response is to bind to a kinase called protein kinase A. Protein kinase A has a regulatory and a catalytic subunit. When cyclic AMP comes in, the regulatory subunit is basically an inhibitor of the catalytic subunit. When cyclic AMP comes in, the regulatory subunit literally binds cyclic AMP. Stoichiometry is more than 1 to 1, we're not going to worry about right now. What it releases is the catalytic subunit, which is active, where this is inactive. And I'll put this down in a second. This active subunit is an enzyme, it's a kinase, it's a serine threonine kinase. Okay, so you see that. Cyclic AMP comes in, binds to the regulatory subunit, releases the two subunits, and you go from inactive catalytic to active catalytic. So it gets rid of, causes the regulatory subunit to come off. Questions on that point? Yes? Yes, it has a regulatory and a catalytic subunit. The enzyme itself is just a catalytic subunit. Catalysis, enzyme, right? Now, what does every self-respecting enzyme have? Substrate. Okay, if there's one thing you learn from today's lecture, it's that. Protein kinase A, unlike the insulin receptor substrate, insulin receptors, is a very promiscuous enzyme. And it phosphorates lots and lots and lots of stuff. In fact, it does it all over the cell. In the cytoplasm, we're not going to get into specific reactions. Remember, when you have glucagon, what do you have? Low glucose levels want to make glucose, right? It converts glycogen, which is a storage form of glucose, into glucose. Okay, so there's actually several steps. But what kicks it on is the pKa, the active pKa. Does phosphorylation events and kicks on a whole cascade of events. In addition, protein kinase A can go into the nucleus. And in the nucleus, it can phosphorylate certain transcription factors, the generic form, that are now active. And these guys sit down on genes that are gluconeogenic. In other words, they're involved in glucose synthesis. So these guys are doing exactly what you want it to do. You have cyclic AMP, you activate protein kinase, goes into the cytoplasm, breaks down glucose, stimulates the breakdown of glycogen to glucose, so you have more glucose to put out in your blood. And it goes into the nucleus, phosphorylates certain transcription factors, you don't need to know the name of these guys, and they kick on the synthesis of genes that are involved in glucose synthesis, which is exactly what you want it to do, because you make glucagon when you have low glucose levels. Does everybody see that? Right? Now, cyclic AMP, we'll get to two issues with cyclic AMP. One is cyclic AMP is your classic secondary messenger. And that is, if you look at a time frame, the hormone comes in, this is the magnitude of the response. First you get a big increase in cyclic AMP, then you get your active protein kinase A, and then you get your response. So don't worry about the shapes of the curves. I just like drawing these kind of curves. I think this is something close to the actual shape. The classic secondary messenger. In that normally you have hormone binds to the receptor, you produce cyclic AMP from adenylate cyclase, you then activate protein kinase A, and then you get a response. In that order. What you can show is, if it's truly a secondary messenger, you should be able to see the response simply by adding cyclic AMP to a cell without the hormone. So they do the experiment. So you have a cell, you give it a membrane-permeable form of cyclic AMP, but don't worry about that, it's called dibutyl cyclic AMP. And you do this without the hormone, and you get a response. That proves all you need to do is generate enough cyclic AMP in a cell, and you don't need the hormone and the regulatory system. The cyclic AMP generates everything I have down on this lower board. Does everybody see that? Classic definition of a secondary messenger. Okay? The other part of this is you can take a cell, and you can either knock out or inhibit pKa, and then add the hormone. So if protein kinase A is involved, and if you knock out protein kinase A, totally knock it out, what would you predict about the rest of the pathway if you kill the enzyme, both either by expression or by inhibition? What would you predict about the rest of this in the presence of the hormone? And we're going A to B to C to D, right? Hormone binds, activated adenylate cyclase, activate through cyclic AMP, protein kinase A. Protein kinase A runs amok in the cell, in the cytoplasm and in the nucleus. If you kill protein kinase A, what would happen with the ability to run amok in the cell and phosphorylate all this stuff? If you kill it or inhibit it, it would happen or not happen? How many people think it should happen? Nobody. Good. How many people say it wouldn't happen? That's exactly what you see. That's our eye clicker experience for the semester, by the way. So you add the hormone, you get no response. So the point is, each of these components are important. The receptor is important, adenylate cyclase is important, the regulation of protein kinase A is important, and all this is important in regulating glucose. Does everybody see that? So we're getting ready for a segue into human reproduction. I got 5 minutes to do it, and it'll happen in 5 minutes in terms of the segue. Okay? Any questions? Okay, so. Yeah, this all is happening sequentially. Exactly right. Sequence, series of events. So let's think about adenylate cyclase. Cyclic AMP is unbelievably important to regulate in a cell. Here's adenylate cyclase. You go from ATP to cyclic AMP. You activate pKa. But in addition, you can turn down cyclic AMP with an enzyme called phosphodiesterase. You get 5' AMP out of it. Now, how many of you had coffee, tea, or chocolate this morning? Any of the above? Okay, I'm a coffee drinker myself. What caffeine does, and theophylline in tea and theobromelain in chocolate does, it inhibits phosphodiesterase. Okay, and also in tea. So when you drink your cup of coffee, what you're doing is you're inhibiting this phosphodiesterase, you're extending your cyclic AMP levels, and you're initiating this response. You're producing, therefore, more glucose, and you get a little bit of that energy burst. It's also the reason you have to go to the bathroom on the half hour if you drink coffee on the hour, for example. There's some connections to diuretic mechanisms. So because of that, they trying to develop a lot of drugs that inhibit phosphodiesterase. Because they thought there was a strong connection to diuretic, producing water, therefore might have a role in blood pressure. Now, where might you test a new novel blood pressure drug? Best place you can think of. An old folks home, right? Because there's a lot of people there that have high blood pressure as you get older. You can talk to your parents if they're on blood pressure meds and so forth. So they tried this novel putative blood pressure medicine at an old folks home in England. Did it for a month, no effect on blood pressure. they went to discontinue the trial, and the place went nuts. They said, no, we want our drug. They said, God, what's going on here? Do they make something addictive and so forth? And they finally figured out what happened. And if I tell you the name of the drug, you will understand. The name of this phosphodiesterase inhibitor was Viagra. Okay, but the men and the women at this old folks home said, no way, we want this drug. So why is this? Why doesn't caffeine act like Viagra? If it did, think of the price of coffee. Okay, and tea. Well, it turns out it's a different kind of phosphodiesterase. It's a phosphodiesterase for cyclic GMP, which is produced by guanylate cyclase, which we'll talk about in reproduction, and this gets converted to 5' GMP. If you inhibit this phosphodiesterase, you have more cyclic GMP around. And what this does, it causes muscle relaxation and vasodilation, which is really another way of saying erections. Okay, and that's what it does. And it turns out there's another place to use this cyclic GMP phosphodiesterase. It's in, I think, the rod cells in your eyes. And you ever see in the advertisements people take Viagra, be careful, you might go temporary blind? It's because of that phosphodiesterase that happens to be in the rod or cone cells in your eyes and causes a temporary blindness if you extend the levels of cyclic GMP. So the point is, what they didn't understand is these are two different phosphodiesterases with two different substrate specificities, one of which allows us to drink coffee and enjoy it, and another one has reproductive effects because of this very similar enzyme with two different substrates, one cyclic GMP, one cyclic AMP. And that is our segue to the next lecture, which is male reproduction. Okay, so enjoy your coffee over the next bit of time. Okay, see you Wednesday.